So now we're going to shift to a whole new topic, so linear momentum and impulse. So we'll begin by talking about linear momentum and building our definition of what that means. So we've been studying objects in motion, so this is going to allow us to analyze it a little differently. And we're going to look at a couple different cases, and then we can build up an understanding of what we're trying to do. And the idea is that if we have a collision, let's make it, well, here, this is going to be our system. We've talked about systems before, but now we're going to talk about isolated systems. An isolated system. And all that means is that nothing else is interacting with it. So there's nothing out here. So this is the system. Everything out here is called the environment. So there's nothing from the environment that's acting on our system. And we do this because then the forces in between them are irrelevant. Those are internal forces. And we've learned before that those don't matter. So there's no external forces, but there's change in motion. If this bowling ball, just put holes on it. If this bowling ball goes rolling down and hits this pin, then the pin is going to go flying off. And so there's been some change in motion, but it's all due to internal forces. So what we want to think about is there some way we can start to think about this and quantify what's happening? Now, the bowling ball, is moving with a certain velocity, usually not very fast. And then when it strikes the pin goes flying off at a much greater velocity. And so there's got to be some relationship here, and that's what we're gonna look at. In particularly, we're gonna look to see if stuff is conserved. And what that means is that there's no change. It's the same before and after. That's what we're going to be looking for. Okay, so the same thing with the golf club. So if you swing the little head of the golf club, which doesn't have a lot of mass, but you swing it around, it gets going pretty fast. I think about 100 miles an hour. And you hit this little ball, then the ball is all of a sudden going to jump out at a very, very high velocity. And so we have some kind of transfer going on here. The system here would be the club head and the ball. That's what we're looking at, not the person. The person acts on the club, but it's the club head that we care about. And then bumper cars. So bumper cars give a great one, and you can see down here, that's what we're going to be talking about, cars colliding. And if we have the same mass here, if we're sitting in there and we both weigh about the same, and we ride towards each other, what do you think will happen when we hit each other? So anyway, we'll get into that, but this is the kind of thing that I was talking about. So here's a little clip of a bumper car collision. And so that's what we're going to be looking at. But if you notice, they're about the same mass, and this is, it's not perfect, but they almost stop. And so it seems like something was destroyed, but we'll see that it's not. Okay, so let's get into a couple little thought experiments, or I guess they're not thought experiments. We actually have some numbers we can put on them. So the way that we draw these, because they're dealing with, there's a collision that happens. So we care about what happens before our initial conditions and then our final conditions. And then we can compare them to try to make sense of what's happened in between. So in this case, we have two cars. They're both the same mass, 0.2. This one's moving with a velocity of 1 meters per second, and it hits this car, which is sitting still, velocity of 0. And after the collision, the first car number 1, has stopped. And car number 2 leaves with the velocity. So you can see this one was moving, it hit it, and then car 2 takes off and car 1 stops. If you've ever played pool, you can make pool shots like this. So we may say, maybe the velocity, it has to do with the velocity, because I see that I have a velocity, my V naught is equal to my VF. So maybe that's what it is. Maybe I have just a change in velocity. Okay, so let's do another one. So now we make one more massive. We put a big one on there. And so this one is twice the mass of this one. And again, it's sitting still. Now, when this car bangs up against it, what we have is the big one continues, but at a lower rate. So it's traveling at 1, now it's at 0.4. And the little one takes off at 1.2. And now that's weird because look, that sum here, the total velocity is 1.6. But we only had 1 to begin with. So it doesn't look like this is true, that the initial velocity or the initial total velocity holds up. So maybe it has something to do with mass. Well, the mass is the same to begin, we have 0.2 and 0.2, and it's the same over here, and we have the same. You don't lose mass. Mass is conserved. There's no pieces flying away. So, but maybe it's tied to that somehow. So here's another example. So now we have our initial velocity, but we're back to the same types of cars. They're headed towards each other. Notice the velocity though. Remember, these are vectors. And this is important when you do these momentum problems. When they collide, if they're going the same speed but in opposite directions, when they collide, they both stop. Okay. So what it is if we could check different quantities. We could add and do all sorts of stuff. But what it ends up being is that if I take the mass of car 1 and multiply it by the velocity. So if I do 0.2 times 1, so that would be 0.2. And then over here, I'm going to do the same thing. So mass 2 V2. And I get 0. And then over here, you can see it's going to flip. So here, mass 1 V1, and that's final, would be 0. And mass 2 V2 final would be the 0.2. So you can see that I kind of have this balance. Okay, so that seems okay if I put it in equal. I can see that this side is kind of equal to that side. But I don't know if it's plus because of the 0. Maybe it's times or minus, who knows. So let's do it again. So 0.4 times 1 is, so I'm multiplying mass 1 times V1 initial. So that would be 0.4 times 1, so 0.4. And then we'll do it again. So mass 1 times mass 2 times V2 initial. That would be 0. I'm going to end up with a 0 again. But now we can check the other side. So this one would be mass 2 times V2 final. So 0.4 times 0.4 is, 0.16? And then we get 0.2. I'm sorry, that should have been mass 1. I'm messing this all up. This is mass 2 times V2 final. So we get 0.2 times 1.2. 0.2 times 1.2. Clear 0.2 times 1.2. I know you can do that quickly, but that's 0.24. 0.24. Now I can see, well, if I add 0.24 plus I get that side. So maybe this is true. So maybe if I add up this mass times velocity on each side, maybe it'll always be the same on each side. So let's check this last one, and then we'll get to our rule. So we're going to check mass 1, V1 initial, and we're going to see what that adds up to if that plus mass 2, V2 initial, and see if that's equal to mass 1, V1 final plus mass 2, V2 final. So now let's plug everything in. So mass, it's 0.2 times the initial velocity 1 plus mass 2, 0.2 times the initial velocity negative 1. Make sure this is where you're going to mess up. Equals mass 1, so 0.2 times 0 plus 0.2 times 0. So on this side, this is all 0, and here, well, that's 0.2 minus 0.2, so we get 0 equals 0. So it assumes that that's true, and it is. It always is. And so this quantity of mass times velocity is called momentum. Momentum. We use a P for it, and it's a vector quantity, and it's defined as mass times velocity. So this is our new topic is momentum. Why P? Because M is taken, I guess. And then N, I don't know. P for momentum. This is on your equation sheet, but momentum is just mv. And it is a vector. So you have to pay attention to the signs because the signs will tell us the final momentum. And then we have the conservation of momentum. Conservation of momentum. And the conservation of momentum just says that the total momentum before is equal to the momentum after final. And these are total momentums. So you could put a sum, but this is typically how I write it. I'll just put P naught equals P final. So then we could just add up what's going on. In our cases, it was like M1 V1 plus M2 V2 plus whatever's left is equal to M1 V1. Oh, these are initials. Final plus M2 V2 final plus whatever's left. So these little ellipses mean whatever else is there. If we just add them up, they're going to be the same on both sides. Okay, so when we talk about momentum, it's a quantity that deals with the mass of the object and how fast it's moving. So objects that aren't moving don't have any momentum. Objects that are going really, really, really fast have lots of momentum. And heavy objects that go slow have lots of momentum. And then you kind of have a combination of them. So you could have, here, look, that's an elephant. Looks like a weird mouse. You could have an elephant running with a velocity, and then you could have a little, I don't know, a little hummingbird moving with enough velocity such that it has the same momentum as this big old elephant, because it has little mass but really high velocity. Or you could have lots of mass and low velocity, and you would have equal momentum. The momentum is a plural. No, momentum is singular. The plural of momentum, just so you know, is momenta. So when we talk about these are the momenta. I usually don't say that. I just say momentum, whatever. But just so you know. Okay, conservation of momentum. So, and this is linear momentum, by the way. So we're just talking about motion in lines. We'll come back and do angular momentum when we do rotation. There's a couple things. So momentum is always conserved. Know that. So it's always conserved. That means that this is always true. It's always equal. It balances out. It's always conserved. If there's no external forces. We'll see what happens when there are. But if there's no external forces, the momentum will always be conserved. The other thing to keep in mind is because it has to do with velocity, it depends on your reference frame, how much momentum. So like this elephant, if the elephant was running along and I'm standing over here looking at it, I would say, yes, it has lots of momentum because it has lots of velocity, because it's moving within my reference frame. I'm going to ignore that bird, but it's moving along the XY. And so I can see, yes, lots of momentum. If you're riding on the elephant, though, probably not lots of momentum because your reference frame is moving with the elephant. So you would say it has zero velocity. So it depends on, it is relative to the observer. But that's it. That's our new topic. So linear momentum. So momentum is always conserved as long as there's no external forces, and it's mv. So we just add them up, and just be careful to take care of your signs. Make sure that if it's negative, everything's good. And that's it, linear momentum.